Okay, so today we are going to discuss how do we model turbulent boundary layers using integral relationships. So the starting point is our discussion we had last week about the inner and outer layers of turbulent boundary layer. And just to recap, the inner layer that contains the laminar sublayer and also the log layer is invariant. It is independent of Reynolds number. It is independent of any pressure gradient. The outer layer is also invariant. Scaled properly, it is also independent of the Reynolds number and is only a function of the pressure gradient. So to make the point, what I did is, so this is a MATLAB file that contains also a direct numerical simulation of an evolving turbulent boundary layer. So what you have is six cross sections over the turbulent boundary layer. So because the boundary layer keeps thickening, initially you have a lower Reynolds number. So this is RU theta. So we have a DNS of a turbulent boundary layer that grows. So we have take 6, 1, 2, 3, 4, 5, 6. And this point we have a smaller theta. So RU theta at this point is nominally is 4,000 and 45,000. So 4,500 and etc. At the end it is 6,000. So we have an evolving boundary layer that keeps thickening. And at every point, the data contains, for example, YD99. That's basically the grid points in this DNS simulation normalized with respect to the 99% thickness of the boundary layer. There is also YP, that is also every grid point, but normalized with respect to Y star. So that's the friction length scale. So for example, this is called a val. So if I take val 1, that's basically a structure that contains a lot of different things. But for example, if you put val1.yp, so that's the y plus normalized with respect to the inner scale. If we plot it with respect to val1 at the same location, same x location, but dot, I want the mean velocity, that is UA. So UA is the velocity normalized with respect to also the friction velocity, U star. So if I plot it, I'll have a plot like that. So the x-axis is y plus, the y-axis is u plus. That's at one single profile. So that shows a characteristic of a turbulent boundary layer. So you have very sharp velocity gradient near the wall, and on the outer side of the boundary layer, the velocity gradient is much shallower, right? That's very different. You can just see clearly that is different from a laminar boundary layer. All right. And to see the profile more clearly, we want to plot which axis in log scale. If you want to zoom in into the inner part of the layer, we want to plot y, which is the x-axis in log scale, right? So instead of having a plot, we do semi-log what? X. That's right. So here it shows it by plotting log, it zooms in the smaller values of y, right? So we see this is a laminar sublayer that we also see in the channel flow, and there is a relatively straight portion that is the log layer. So the entire inner part of the boundary layer is described by the Spalding profile. And let's just to see the universality of the inner layer, let's plot all of these different profiles. Let's plot all of these 6 snapshots on the same plot.
Is there a pressure gradient?
Oh, it's a flat plate, so pretty much 0 pressure gradient. Right. Okay. So let's do a loop. Hold on, and for I goes from 1 to 6. Let's do a semi-log plot of I.yp val I.ua. So this is how it looks like. We have seen, well, there are 6 different velocity profiles, but they all collapse on top of each other all the way to here. So this is what the inner layer looks like, the laminar sublayer, the relatively straight log layer. I mean, plotted on a semi-log scale. If you have a straight line, that's a logarithmic log. All right. So this is the inner layer. Questions? Nope. Okay, good.
Which one's station 1 and which one's station 6?
Oh, that's a good question. Which one do you think is station 1? Which one do you think is station 6?
The top one's no, the bottom. The top one's station 6.
The top one is station 6. Why is that?
Because the wall shear stress is lower, and it's the same edge velocity. So if you divide, the new star is directly proportional to
You're right. So the top one is the last station. The bottom one is the first station. The top one is the last station. So why is that? This is because the free stream, or UE, is the same for all these stations, right? So if you didn't normalize by the friction velocity, the flat region of the profile is the same. That means the top one has a lower friction velocity, and friction velocity is proportional to the square root of tau. So the top one, the top profile, is going to have a lower tau. As you move along the flat plate, the skin friction decreases as the boundary layer thickens. So the top profile is at the highest RE theta, or the latest position in the boundary layer.
But the UE being uniform, is that physical? Or is that imposed? Or?
Yeah, UE being the same is imposed because the DNS is simulating a flat plate. It's simulating the boundary layer over a flat plate. So UE is pretty much the same along the way, or at least the simulation tries to control UE to be the same. Okay, so this shows the inner layer.